on Earth's upper atmosphere.
This meeting is being recorded.
Professor Ludger, his primary interest is on the specification and forecast of effects of the solar storms and the ionosphere-thermosphere system using data assimilation techniques. He is the chairperson of International Space Weather Action Teams, ISWAT, Global and Regional Ionosphere Total Content, TEC, Group, and chairperson of the International Community Coordinated Modeling Center, Living in Our Star, CCMCLWS, Working Group on Regional and Global TEC. Professor Ludger, thank you a lot to accept our invitation to be here. And now here, you can start your talk. Thank you very much.
Well, thank you very much, Geraldo, for the introduction. And also thank you very much for inviting me to talk today about data assimilation for space weather models. And probably space weather, it's something that most people of you are not familiar with. So I hope at the end of this talk, you're going to have a good feel for what space weather is all about, and the way we're approaching the modeling efforts of these phenomenon. So if you think of space weather or of space, it's certainly a very vast region. If one thinks, well, NASA deals with space or the European Space Agency deals with space, you think of very vast regions that include the sun, that includes the interplanetary space, the interplanetary medium, that includes the Earth, that includes the region around the Earth that we typically call the near-Earth space environment. And there are magnetic fields that play a role. You're going to see electric fields play a role. Lots of things that matter when we think of space. And of course, modeling this region as one whole thing is a near impossible undertaking. And based on that, these regions often separated into different regions, people that study the sun, that model the sun. And there are, in fact, data assimilation models for just the sun, or models for the interplanetary space, for the interplanetary medium, for the solar wind. Going to talk about that. There are models for that. Very, very difficult to model. And that is because there are just very few observations available for that region. And then we come closer to Earth. Closer to Earth, we have more observations. We have satellites that orbit around the Earth, that take observations. We can take observations from the ground. And with that, data assimilation becomes much more feasible than for the outer regions of space. And as a result of this, space weather models that have been developed over the years mostly deal with the near-Earth space environment. And the near-Earth space environment also includes parts of our atmosphere. The upper parts of our atmosphere, and that's the space weather that I'm mostly going to talk about today. So let's just talk a little bit about our atmosphere to get a feel of what is the region that we're dealing with, what is the region of interest for this presentation today. And let me just go here, and if you think of our atmosphere, that's of course by itself a vast volume, and typically and commonly this region is divided into different layers. And this classification of the atmosphere is typically based on the change in the temperature with altitude. Now, what is the temperature doing as we go up from the ground in altitude? And on the left here, you see a graphic here where we have on the y-axis altitude, on the x-axis is the temperature, and you see here the temperature profile as you go up here, let's say to 1,000 or 2,000 kilometers in altitude, and you see that this temperature is changing with altitude. This is, by the way, a log scale on the y-axis here in altitude. Yeah, and probably most of you know, if you climb up a mountain, the temperature is decreasing. It becomes colder as you go up in altitude. Yeah, and that is characterized by a drop in the temperature or a negative gradient in the temperature. The temperature is falling off as you move up in altitude. And this trend goes on up to about an altitude of 10 kilometers. That's an altitude where, well, where the altitude where most planes fly. And this region is called the troposphere. So we are living in the troposphere, and most weather models that you had heard about, during the past days, they deal with the troposphere. Now, it's this region where the temperature decreases with altitude. Now, once you reach 10 kilometers, you reach the tropopause, and at that altitude, this trend changes. And it changes due to the absorption of ultraviolet light that comes from the sun by ozone. And as a result of that, energy gets absorbed, and with that, the temperature increases. And that's this region here from about a 10-kilometer altitude up to about 50-kilometer altitude. That's called the stratosphere. So the stratosphere is a region where ozone absorbs ultraviolet radiation, leading to an increase in the temperature. Yeah, at about 50-kilometer altitude, the atmosphere runs out of ozone, and with that, this process does not take place anymore. Yeah, and as a result of that, the temperature decreases again. Yeah, from about 50 kilometers up to about an altitude of 100 kilometers. This is called the mesosphere. Yeah, the mesosphere lacks mechanisms to absorb radiation from the sun, and with that, the temperature decreases. And again, that changes at 100 kilometers. And at 100 kilometers is about the region where we say, well, space begins. This is the region now where we make our way into the thermosphere. And the thermosphere is characterized by now a strong increase in the temperature. The temperature increases here dramatically due to the absorption of ultraviolet light and extreme ultraviolet light, and so on. And you reach temperatures here of 1,000 or 2,000, or maybe sometimes even 3,000 Kelvin. Yeah? Now, this region of the thermosphere, this region where we have this increase in the temperature, will be the focus, or the main focus of this presentation. So from about 100 kilometers on upwards. Now, this is the region also where most satellites fly. Now, the International Space Station orbits at around 400 kilometer altitudes. That's right in the thermosphere. Yeah? And let me just talk a little bit more of this. So let me just see, I have here, it has been enabled. Okay, let me just talk a little bit about this region that starts at about 100 kilometers. We had seen, that the temperature strongly increases here from about 200 Kelvin at 100 kilometers, reaching temperatures of about 800 Kelvin, and that can go to 1,200 or 2,000 or even 3,000 Kelvin, depending on what the sun is doing. So the temperature at this region strongly increases, and it becomes highly variable depending on what the sun is doing, how active the sun is. Yeah, and I come back to that in a moment. At this region, also the gas species will begin to separate according to their mass. If we look at the composition of the atmosphere, we look on the ground, it's about 78% nitrogen, 21% oxygen, O2, and there is some argon, yeah, and some other minor species, CO2, of course, and that composition, and of course the density changes, but the composition stays about the same up to an altitude of about 100 kilometers. Yeah, and at that altitude, now things change. And that changes dramatically in a way that now the gases separate according to their masses. Now, so the more heavier gases like N2 and O2, they drop faster than the other species that are a little bit lighter. You also see here that atomic oxygen becomes a very prominent factor or gas at this altitude, which doesn't play a role at the lower altitude. Lots of hydrogen, we have helium at this region that eventually become also very important species. So the composition changes dramatically at this altitude. Lots of things change. The physics of the atmosphere, in a sense, changes. Below 100 kilometers, the atmosphere is turbulently mixed with that constant composition, and that process stops at about 100 kilometers, and the gases start to separate according to their masses. Yeah? Now, embedded in this neutral atmosphere is an ionized part. Yeah? An ionized part. Now, charged particles that consist of ions, consists of electrons, that is embedded in the neutrals. So the neutrals play the main role here. You see here we have the density on the x-axis here as a function here of altitude. You see the neutrals here. You see embedded about a factor of 1,000 less than the neutrals, the charged particles in this region. Here, for example, the electrons. And this is the distribution of the electrons in this region with altitude. And you see a whole host of different ions that play part in this region. You also see here that the peak of these ionized or charged particles is about at an altitude of 250 and then 300 kilometers, just to give you a feel. So roughly at an altitude where the International Space Station orbits, the International Space Station is about here at 400 kilometer altitude. Yeah? So this region is called the ionosphere. The ionosphere, you're going to see, plays a very important role on a host of technological systems, the GPS system, communication systems, and so on. And that's why we're very interested in having models and having weather models for the ionosphere. And I'm going to talk mostly about weather models, data assimilation models for this part of the atmosphere, the ionosphere. Yeah? So when you look at this profile here, it turns out that this is kind of a typical profile, but it's by no means always like this. This profile changes quite a bit. And that has to do with what the sun is doing. Yeah? So let's think first what creates this ionization. Well, this ionization is created primarily by radiation coming from the sun, solar extreme ultraviolet radiation, as well as X-ray radiation. Now, solar extreme ultraviolet, or EUV, and X-ray that come from the sun are highly variable. Depends a lot on what the sun is doing. Now, how much EUV radiation and how much X-ray radiation comes from the sun. There are times when the sun is very active, and there are times when the sun is very quiet. Yeah, and this varies on several time scales. There's the L10 year solar cycle, for example, where it goes from solar minimum to solar maximum. And during that time, the extreme ultraviolet and the X-ray radiation changes by orders of magnitudes. Now, what comes from the sun, and with that, the ionosphere changes a lot. But the radiation from the sun is just one thing. There's also particles, electrically charged particles that come from the sun and that engulf the Earth and have a strong effect on the Earth's upper atmosphere. So this region above about 100 kilometer altitude. So it's electromagnetic radiation, extreme ultraviolet radiation, and the X-rays, as well as particles that come from the sun that create weather in the Earth's upper atmosphere. Yeah. Now, there's a whole chain of events as the particles come from the sun that is involved in creating this weather. But the main part is that the electrically charged particles often also called the solar wind. It's a constant stream, kind of an outgassing of the sun that's sent out into space. That interacts with the Earth's magnetic field, and with that changes the atmosphere. So you have the solar wind here coming from the sun, a constant stream of electrically charged particles. So these are not the electrically charged particles I talked about before. Those are down here in the ionosphere. The ones created in our atmosphere. These are differently electrically charged particles coming from the sun that constitute the solar wind. They eventually, 150 million miles later, reach the outer parts of the Earth's near space environment at about 50,000 kilometers away from the sun, where they encounter the magnetic field of the Earth. And these particles interact with the magnetic field. They compress the magnetic field on the sunward side, on the day side, you can think of, and they elongate this region, the magnetic field of the Earth on the night side, and they elongate this, in a way that if the moon is on that side, for example, the moon would be inside of this region. Now, this region is called the magnetosphere. And that's the first region that's encountered by these electrically charged particles. And that are now changing what's going on here and creating space weather. Now, the solar wind is always there. That is this outgassing that comes from the sun, but sometimes, and especially during solar maximum, meaning during this 11-year cycle when the sun is more active than during quiet times, during solar maximum, the sun sometimes becomes especially active for a day or two. And this is called a solar storm. And during these times, very energetic processes happen on the Earth, on the sun. And you see here, this is the surface of the sun. There's something going on here. There's a large amount of material thrown into space here. And during these times, you have this material thrown into space. This is called the coronal mass ejection, or a CME. And you also have so-called solar flares, large solar flares that create extreme ultraviolet, X-ray, and even gamma ray radiation that makes its way to the sun, to the Earth, if we're in the way. So during a solar storm, there is massive amounts of solar material thrown into space. Now this light then reaches the Earth. So that's from a solar flare. The light reaches the Earth in 8 minutes. That's the speed of light, 300,000 kilometers per second. The distance is 150 million kilometers. So it takes 8 minutes for the light to reach the Earth. And for the material that comes from this CME, it takes longer. It's also very fast, about 400, 500 kilometers per second, but it takes about a day and a half, or sometimes 2, sometimes 3 days to reach us, depending on its speed and its speed that it's thrown out into space. And it also only reaches us if it's thrown out in our direction. And sometimes it misses us, but when it hits us, it creates large weather in the upper atmosphere, and that's the weather that I'm talking about to a large extent. But just to give you an idea of the sheer amount of material that comes out of these coronal mass ejection, I just show you here a size comparison. Here's the surface of the sun. This is the photosphere that we look here, and you see here this region of this large outburst of material here that's thrown out into space. A solar storm, solar eruption going on here, and embedded here is the approximate size of the Earth. This is not the location of the Earth. The location is many 150 million miles away from the sun, But just to give you an idea about the size, it tells you really who's boss here. If this material is thrown out into space and eventually hits the Earth's magnetosphere and eventually changes the Earth's upper atmosphere. So the Earth is only inset here to show scale. Okay, so once this material now hits the Earth, there's a lot of weather going on. So what we see here, the sun is here on the left. You don't see this, but you're gonna see, I animate this in a second. Now you're gonna see material coming from the sun. Now this is the Earth here, and this is the Earth's magnetic field here, compressed on the sunward side, talked about that, and elongated on the night side here. And now let's see, we often think of the Earth's magnetic field. Well, that's a static thing. You use a compass. That's all good, close to home, close to the ground. But when you go out in space, I want to show you how much weather, how much variability there is. So take a look at this, how the magnetosphere changes as this material here comes from the sun. That's the space weather that we're talking about. Let me animate this again. Let me also point out this inset down here. This is when you are at high latitudes and you will look up, up into the sky. You would see aurora associated with this event, and that's also a manifestation of this material, or a result of this material coming from the sun. And let me show this again, and you see the variability in the aurora here, giving you an idea about the weather variability in the upper regions of the Earth's atmosphere and in the magnetosphere. So that's a type of weather that we're talking about. So once this hits the magnetosphere goes like a flag during a windstorm, wobbles around, and that now changes many things as we come closer to Earth. We come to this region above 100-kilometer altitude to, let's say, a few thousand-kilometer altitude. There are several chains that now physically change this region. There's the radiation, the change in the radiation, changing the ionization in the upper atmosphere. We're seeing, the ionosphere reacts to the change in the extreme ultraviolet and the X-rays. There's a solar energetic particle chain that, for example, creates parts of the aurora. There's the solar wind magnetosphere chain. Lots of things going on here. There are currents involved in here. There are electric fields involved, electric field driven. E stands for electric fields involved. The magnetic field of the Earth plays a big role. We had seen this. So there are lots of physics going on that now creates weather in the upper atmosphere when the sun changes its doing. And there are eruptions on the sun, or even during quiet times when things change on the sun. The sun is not as constant as one often thinks. There's lots of variability going on there. So this is what comes from the sun. But there's also things or energy and momentum coming from the lower atmosphere. And from the lower atmosphere, I mean that even from the troposphere or from the stratosphere. And this region, you see here the lower atmosphere, you see here the thermosphere ionosphere system. And the way that the lower atmosphere influences the upper atmosphere is through waves. There are waves generated in the lower atmosphere that make their way up into the upper atmosphere and create variability, create weather in the upper atmosphere. Now, these waves are in the form of so-called gravity waves. Now, gravity waves can be created, for example, when you have a wind blowing against the mountain, that disturbs this wind flow, and there are waves created from this. I know that I live close to Salt Lake City, and when you fly from Denver to Salt Lake City, you cross the Rocky Mountains. And the Rocky Mountains, there's a constant wind blowing against the Rocky Mountains, creating gravity waves, these waves that propagate upward. And when you fly over this region, it becomes very bumpy on the plane. And that's the effect of these gravity waves created in the lower atmosphere here. They're also created by thunderstorms and many other things. Yeah, and some of these gravity waves make their way into the upper atmosphere and create weather in that region. There are also other waves, tides, for example. Tides, you're familiar from the oceans with tides. There are also tides in the atmosphere generated by absorption of solar radiation, and also by the gravity of the moon as the ocean tides. And these tides also make their way into, or some of these tides make their way into the upper atmosphere. They're planetary waves and other types of waves that make their way into the upper atmosphere and creating weather at that region. And all that is called space weather, once we're above about 90 or 100 kilometer altitude. Yeah. Now, this just shows you here some measurements, where we look at some of the charged particles, for example, helium, charged hydrogen, or charged atomic oxygen, O+, H+, and He+. And you see here, this is altitude, concentration versus altitude. You see the variability in the concentration here, in helium here, it goes over an order of magnitude, factor 10 variability. And a lot of this comes from what the sun is doing. In O+, there's a variability factor 2 or factor 4 is not unusual from one day to the next, to see variations in the density. So a lot of weather going on in this region. And that's the type of space weather that affects. Yeah, that there was someone was talking. Was there a question or?
No. It's a kind of noise. I'm sorry about that.
Oh, okay. Okay, that's the type of weather that also affects technological systems. Now let's take a look at this for a second. For example, this region of the upper atmosphere, is the region, the environment where many satellites, where, for example, the international. Could maybe everyone mute their microphone?
Yeah, I think that there is someone who has a microphone open. Please close your microphone.
Okay. Thank you. Thanks. So this is the region where many satellites operate. And for example, the International Space Station operates. And when we have the space weather going on, these satellites sometimes get even lost, and we need to find them again. Yeah? The International Space Station constantly experiences a drag from this region. Even though the densities are very low, they still, over time, drag the International Space Station. And as a result of that, the station needs to be raised once in a while. That's typically when some other spacecraft docks to it, it pushes it up, or it also has ways to push it itself up by itself. Now, if it wouldn't do that, it would have re-entered a long time ago. And when there is space weather, then things become much more variable. And as I said, sometimes satellites even get lost during the storms. It's also a region, where navigational systems have to cross through. You're all familiar with the GPS system. I'm sure you all have a cell phone, and if you want to know where you are, have a GPS receiver in your cell phone that talks to the GPS satellites. The satellites are at some 22,000 kilometers above the ground, so they are above the ionosphere. But the signal has to go through the ionosphere, and it gets modified as it traverses to it, and that leads to problems in the navigation system, and that low latitudes, equatorial latitudes. For example, in Brazil, I know there are many people in Brazil, that sometimes in the evening hours, GPS even becomes unusable due to space weather going on, so-called scintillations. Yeah, so these systems have to cross through the near Earth space environment, the upper atmosphere, and they get eventually, sometimes strongly affected by this, to the extent that it becomes unusable. Yeah. On the other hand, this region protects us against extreme solar electromagnetic radiation and also against particle radiation, because it absorbs. We've seen this, that the solar extreme ultraviolet, that the X-rays, they get absorbed at this region. So there's also something good to it. Now there are also effects here on the current, on the electrical grid. For example, pipeline corrosion. All this comes from space weather, or to some extent from space weather. So lots of technological problems affected with this. So how can we absorb this? Since this system changes, for example, a GPS signal that goes through the ionosphere, now we can use this, on the other hand, to learn about the ionosphere or to observe the ionosphere. Or we can send electromagnetic radiation from the ground up into the ionosphere, and look at what's reflected back. So there are ways how we can look at this region from the ground. For example, we can get electron density profiles from an instrument that's called an ionosonde. Show you in a second how that works. Or we can use GPS or other so-called GNSS. This is the Global Navigation System satellites. So that's not just GPS, it's also GLONASS, the Russian system, or the European system, or Bijou, the Chinese system, that one can use to obtain measurements of or information about the ionosphere. One can measure the density, the ions, the charged particles along satellite tracks with in situ observations on satellites, or one can look at natural emissions from this region with optical instruments on satellites, or something that's called a radio occultation. And let me just tell you a little bit about these observations, and also how some of this, needs to be taken into account, some of the issues with this data when you do data assimilation. So let's just look at an ionosonde. An ionosonde is an instrument that has been around for a long time, almost 100 years. It was when it was first used, a very simple instrument in a sense. Where you have a transmitter on the ground and a receiver on the ground, where you send an electromagnetic wave, a short pulse, high frequency signal, an electromagnetic signal, a radio wave, straight up into the ionosphere. And this electromagnetic waves now sees the electrically charged particles in the ionosphere. So you have these charged particles here. There comes an electromagnetic wave, electric fields, magnetic fields. They are affected by the ionization in this region, and as a result of this signal is reflected back to the ground, for a certain frequency. If you use high frequency, let's say 6, 7, 8, or 9 megahertz frequency, in that range, it's reflected back to the ground. Now that reflection that occurs at an altitude where the natural frequency of the charged particles in this region matches the frequency of the radio wave propagating up. So the wave propagates up, interacts with the ionization up here, makes it oscillate up and down, and when that natural frequency of the charged particle matches the frequency of the signal, then the signal gets reflected back to the ground. And one then records the time delay between the transmission and the reception of the pulse, and one can tell how high the signal went, and based on the frequency, one can tell what is the natural frequency of the ionization at that region. And that, in fact, on the other hand, is a function of the density itself, of the charge, the density of the charged particle. Very simple measurement. Now let's think one would do this at not just one frequency, but one would scan through the entire range of frequency. Then one would scan along an entire profile here. Now you see here, you're changing the frequency. You're increasing your sounding frequency. This is the typical profile of the ionization. I showed you that before in the upper atmosphere. And depending on for the lower frequency, you get a reflection from the lower parts of the ionosphere. And now as you increase the frequency, you probe different altitudes of this layer up to the peak. You do not get any information about the top. Only of information about the top, about the bottom side, about the bottom side profile. So now you have these individual measurements here. And of course, if a signal gets reflected here, it had to transverse to the lower part of the ionosphere. And it already got modified, got somewhat changed, affected by these lower parts. So to tell you exactly what the density is at a certain altitude here, or in other words, or also what the altitude is of the reflection, one has to know what the density is below. So if we have a measurements here, this measurement depends on what's below. And this leads to correlated errors in the observations. We measure the bottom side profiles, but as we make our way to where the errors that we get become correlated. And that's for data assimilation, of course, a very important thing. I'm sure you had heard a lot about the Kalman filters over the past days. There is something that's called the measurement error in the Kalman filter. That plays a critical role in the Kalman gain, the R matrix. That R matrix is often, we have that's the measurement errors in there, and often they are assumed to be uncorrelated. But in this case, these errors become correlated. And that's an important thing to understand and to put into your data assimilation system. So you have to understand exactly the measurements, how they are made, and to put this properly into your data assimilation scheme. Now this is for an ionoson. Let me show you another observations that we have, and that is the measurements from the GPS system. I told you before that these GPS satellites, they are of course used for navigation purposes. They're at about 22,000 kilometer altitude, and the signal from the satellite, let's say you're on the ground here at some location X here, and with your cell phone, and you're looking to one GPS satellite and maybe a second one and a third one, and based on the signals that you get from these satellites, you can tell where you are on the ground. You can use this for navigation. But these signals have to go through the ionosphere, through these charged particles, through these charged particles, and that changes the signal. And with that, your navigation becomes somewhat erroneous. Now, those errors can be in the centimeter, or sometimes in the meter range. Typically for a cell phone, that's not a big deal. But for some technical applications, you want to land a plane, for example, these become very, very important. And that's an effect of the ionosphere on the GPS, on the navigation. But as an observation, we turn this around and we use this uncertainty or this change in the positioning to tell us what the ionization or what the medium was that the signal has traversed through. So we turn the problem around, the annoyance that this region leads to an uncertainty in your observation. But if you know exactly where you are, you have a receiver on the ground that you know exactly where it is, but now if your navigation tells you, well, you're actually somewhere a little bit off, then you can use that information to tell you something about the medium that the signal has propagated through. Yeah, and these observations created a very large boom in ionospheric observations, that came with the advent of the GPS systems, because there are now so many GPS receivers on the ground, thousands of them. Of course, these satellites here, the GPS satellites, they're not static. They're constantly changing. Typically, you have something like maybe 7, 8, 9, 10 satellites in view that you could use to pinpoint your navigation. You need 4, and you use the others to reduce your error. Let me tell you a little bit more how we get the information out of this. Yeah, and that is we're measuring something that's called the phase of the signal. Yeah, the phase of the signal, that's a certain measurement of character of the signal that's received. One can measure this, and that's affected by several quantities. This equation down here, let me just tell you a little bit about that. For example, what goes in there is geometric distance between the transmitter and the receiver. The transmitter is out in space. The GPS satellite, it's moving. You're on the ground. So this is changing with time, but it does not depend on the frequency. Example, there's a timing difference. The signal has to travel from the satellite to the ground. C is the speed of light. Delta T is the time it takes. So that's also related to the distance that the signal traversed through. And there are other disturbances that lead to changes in the phase that come from the troposphere, so the lower part of the ionosphere. Humidity, for example, is something like phase cycle slip, multipath ambiguities, and there is noise associated with instrumental transmitter and receiver calibration parameters. Lots of things that go in there, and most of them do not depend on the frequency that the signal has. So these are to large extent frequency independent terms. Certainly the first two are frequency independent. But there is this one term here that depends on the frequency, and that has to do with the ionospheric effects on this measurement of the signal. And this depends on the frequency of the signal that comes from the GPS satellite. So that frequency that depends on the frequency. So now, if we look at the signal that comes from, or the signals that come from a GPS satellite, we see, well, there's not just one frequency. In fact, 2 frequencies, or some newer have even 3 or 4 frequencies that they transmit at. Now, if you have a receiver on the ground that can look at 2 of these frequencies, let's say the L1 and the L2 frequency. These are at about the 1.3 gigahertz, 1.5 gigahertz, and one can use this to get information about the ionization that the signal has traversed through. So we have these. We can now take then differences of 2 measurements, and we can subtract them, and we get information about the total number of electrons that the signal or the radio wave saw as it made its way from the transmitter toward the receiver. So that's our measurement. It's an integral measurement. And that's, of course, something that's when we do data assimilation, we have to come up with something like the H matrix in the Kalman filter. We have to take this integral here and put it into a numerical way. We call this the total electron content between the transmitter and the receiver. Now, I said that this term here, this epsilon, that many of the things that go in there, this error, this noise, Most of these things are frequency independent and they cancel out, but not all of them are. There are transmitter and receiver dependent biases that depend on the frequency and that depend on the transmitter. So it's not just DC here, but there's also a bias that comes that is added to it. And this bias depends on the receiver. So if you have a receiver on the ground at one location and a receiver on the ground at a different location, those biases are different. They're not the same. Now, each instrument has its own bias, and even worse, this bias can change over time. Some of them are even temperature dependent. And this is something, when you do data assimilation, that needs to be taken into account, of course. Now, there are different ways how people deal with this. One way is that it's determined, estimated before the data assimilation process. But there are, of course, assumptions going in there that might not be consistent with your data assimilation scheme. And in that case, you're running somewhat into trouble. Another way would be to include the estimation of this bias in the data assimilation process itself. So in our case, typically the state consists of the electron density. But we're solving then for the electron density, but we're at the same time, we're also determining these biases. This is done through an augmentation of the state. Now, the important thing here is that there are thousands of these receivers. So that means you have thousands of biases that you need to determine. That's, of course, adds quite a bit to the complexity. Now, another thing that I like to point out here is that the observations are pretty dense over the continents, over at least the American and South America here, over Asia, a fairly dense network, over Africa, regions with where we only have very sparse data, but you see that over the ocean, these are ground receivers, but over the oceans, we basically have no observations or very sparse observations. Also, it's seen you get this integral from this, the integral over the electron density from the transmitter to the receiver. So we don't have any height information, or very limited height information that's in these measurements. Now, when you do data assimilation, now, of course, a very strong or very powerful way is to combine this now with other observations. And what we're doing is that we're combining this with a different type of observation that also uses GPS the GPS system, but now the receiver. Think of your cell phone not on the ground, but you put your cell phone on a satellite. You put it on a satellite that's in low Earth orbit. In low Earth orbit, let's say at 300 or 400 kilometer altitude, it takes about 90 minutes for the satellite to go once around the Earth. The GPS satellite up here at 22,000 kilometer altitude takes 12 hours to go once around the Earth. So as the low Earth orbit satellite moves maybe from here to here, the GPS satellite basically doesn't change up here. Just very, very little. And with this, you get different scans through the atmosphere. This technique is called radio occultation measurement. And you see here that you get the total electron content through this scan, you get it through this scan and through this scan, and you can use this this can be inverted using an Abel inversion, for example, to tell you what the electron density is, or you can use these observations directly in your assimilation scheme, and you might get the idea here that this also provides height information throughout the atmosphere. So there, of course, comes the strength of data assimilation, to combine observations with different strengths and weaknesses. Of course, we don't have this many observations. For radio occultations, very many from the ground. But this, on the other hand, provides us altitude information, very, very important information. Yeah, so we have on the one hand large amount of data, it's quantities of data, with different kinds of instruments that measure different quantities. And it's sometimes like comparing apples and oranges, or combining apples and oranges. The observations are in different places. The observations have different cadence, have different availability, and they have different error statistics. I told you, some have biases involved, some of them are correlated. So it makes it very difficult to create a coherent picture just from the observations alone. Now, on the other hand, we have fairly mature theoretical numerical models for the upper atmosphere. And these models, to a large extent, contain our knowledge of the physics, or what we can put in these models, what we can program. Yeah, and just to give you an idea what these equations are, some of you might be familiar with similar equations. There's a continuity equation that tells you how, let's say, the density, let's think of the density of the electrons, for example, change due to transport processes, because they are moved away, and production and loss processes. EUV production, but there are also loss processes involved here that are covered by the continuity equation. There's a momentum equation or a force equation that tells you how the momentum changes depending on the acting forces, pressure gradient forces, gravity. There are electric fields play a very critical role here. We are dealing with charged particles, and they react to electric fields, but also the Earth's magnetic field is important here, and collisions between the neutrons. And then there is an energy equation that tells you how the pressure or how the temperature changes, maybe due to collisions, heating, and cooling processes. Yeah, so we have this set of three equations, and typically these equations are solved in the magnetic coordinate system. So the Earth's magnetic field plays an important role here. Yeah, and that's, we're going to see an important thing for certain things in our data assimilation. Yeah, for example, the motion along the magnetic field, perpendicular to the Earth's magnetic field, is driven by electric fields. Now, E here is the electric field, the so-called E cross B force. Don't worry about that. That's a force that's driven by electric fields, and it's perpendicular to the magnetic field. Motion along the magnetic field. Now we have here, this is just here, a field line, magnetic field line here from the Earth, geographic latitude and altitude here. Motion along this field line here. Now that's basically a diffusion equation if you look at these equations. Yeah. Now you see here that the motion of the charged particles very strongly controlled by the Earth's magnetic field. Yeah, and that means that correlations that we're going to use in the data assimilation are strongly influenced by the Earth's magnetic field. That needs to be taken into account, when setting up the problem. Now, just as one example here, this is something called the equatorial anomaly that comes from electric fields. These electric fields, some of them come basically straight from their interaction of the solar wind with the Earth's magnetic field. Some are created internally, some are come externally, of many sources. These electric fields, if they are here, we have charged particles. Let's say here's the northern hemisphere, it's the southern hemisphere here. This is the magnetic equator. It's a little offset from the Earth's geographic equator. In Brazil, it can be 5 degrees or so, offset there from the geographic equator. And when we are at 100 or 200 kilometer altitude, and we have this electric field, and it pushes ionization up in altitude. It's perpendicular. If we have an electric field coming out, it's pushing ionization up, and that ionization then diffuses along the magnetic field, creating crests on the northern and on the southern side of of the equator, roughly at a distance of, let's say, 15 degrees on either side. So we have a separation of 30 degrees here between the southern crest here and the northern crest. 30 degrees, that's about 3,000 kilometers. So we have correlations along the magnetic field here that can be 3,000 kilometers and more, and that can, these processes are fairly quick. That, of course, needs to be taken into account. There's also a neutral wind often blowing. The neutrals now drag the ions that collide with it and push some again along the magnetic field on the other side. Here, for example, a wind blowing from this side here pushes the ionization up here, pushes it down on the other side and drags this over here, now creating large correlation lengths in this region. And that is in one direction, along the magnetic equator. That needs to be taken into account. So on the one hand, we have these theoretical models that contain our knowledge of the physics, but these electric fields and the winds that I showed you there are only very few observations of these, so they're largely uncertain. So we have many uncertain parameters in this physics-based models of electric fields, neutral winds, the neutral composition, and so on, as well as initial conditions, that just having a physics-based model is just no good. And that's, of course, now where data assimilation comes into the picture, where the objective is to optimally combine the observations and the model to create a coherent picture of the space environment. So that's where this comes into the picture. And now over the past years, there are several data assimilation models that have been developed that also employ various assimilation schemes, various complexity in terms of the assimilation. There's a so-called band-limited Kalman filter. It's been created by the Jet Propulsion Lab, by JPL. Band-limited means that correlation lengths, if you have a latitude, longitude, altitude grid, that you have the diagonal elements, and then you have maybe the first of diagonals and the second of diagonal elements, but all the others are set to zero. It's band-limited Kalman filter. I'm going to talk somewhat about the Gauss-Markov Kalman filter. That's also a simplified Kalman filter for this region. There was a reduced state Kalman filter developed, as well as ensemble Kalman filter. I'm going to talk a little about that too, and also 4D variation models that have been developed. So all these have different strengths and weaknesses, of course, and for all of them, the specifications that these models provide are for the ionospheric plasma densities. So the O plus density, the H plus density, and the electron densities. And some of these also give you information about unobserved parameters, like the electric fields, the neutral winds, the neutral composition, that are not directly observed, but that are estimated in the data assimilation process. So let me just talk first about the Gauss-Markov Kalman filter. The Gauss-Markov Kalman filter is really a pretty simplified Kalman filter approach, where we're starting from a background model, where we have an ionospheric model. It's called the ionospheric forecast model, the IFM, that contains our physics, but it has uncertainties. It doesn't know what the electric fields are, doesn't know what the winds are, except for climatological values. It doesn't know what the initial conditions are. Just a physics-based model, just a free run of a physics-based model. And now the Kalman filter solves for deviations from this background field. And these deviations are propagated forward in time based on a statistical process. Now that's the Gauss-Markov process there. Now, what you gain by doing this is that your state transition matrix becomes a diagonal matrix. That's the M matrix. When you talked about the Kalman filter, that becomes diagonal, and that of course makes things so much easier and so much more computationally tractable. That we can run this on 1 or 2 CPUs if we don't for global run if we don't go to too high of a resolution. The disadvantage of this is that the model does not give you any information about the driving forces. It really just tells you something about these deviations from the background field, the deviation in the electron density, for example. So that is something that can be built fairly straightforward, but there are certain things that one needs to take into account here. And one thing is, that you have this background model, and you're looking for deviations from the background field. So you don't, let's say you don't have data. If you don't have data, then you just get the background field. What you would like to have is that becomes unbiased. That you basically get an unbiased background. So a large amount of work that we had to put into developing this was the elimination of biases in the background. And the best way to do that is, of course, by comparing the model data with observed observations. And for that, again, we use this TEC, or the total electron contact, from a satellite that's typically being used for measuring the ocean, the sea surface height, the TOPEX satellite here. That's now the JSON satellite, but we use some older data here from TOPEX. Well, that's measurement where you have a transmitter on the satellite, TOPEX, sending a signal, radio signal, down through the ionosphere, and then observing reflections from the oceans, and getting from there the sea surface height. But this signal has to go through the ionosphere. They again do this at 2 frequencies. And just as I outlined before, one can calculate the total electron content from this. One can also calculate it from the physical model, from the IFM, and compare this. So these comparisons were made over the oceans. We had 10 years of data, 11 million measurements that covered different seasons, different solar cycles, different solar activity conditions. It's also often called magnetic activity condition, but this is what the sun is doing. And by comparing these, we adjusted uncertain parameters in the ionospheric forecast model to bring this model into better agreement with the observation. Now, a very important step in developing this Gauss-Markov model. This just shows you here an example of this. Is for winter. The sun is very there were no storms going on. That means low KP. But it was solar maximum condition in the 11-year cycle. Up here you see the TOPEX observations over the oceans. That's the white spots here is where you had land masses. And the corresponding model TC, and you see large deviation, large differences here. For example, in this region here near Australia, totally off. So this needed to be corrected, that we could use this as a background model. And you see here the differences, the relative differences before the adjustment and after the adjustment. Very important step, was not perfect, but it led to much better model performances. Important thing to do. Second thing that you have to worry about is the process noise. This model uses a statistical process, the Gauss-Markov process. So what to use for the process noise, or in the Kalman filter, that's the Q matrix. That tells you for the uncertainty, or the noise of your forward model. Now the idea there was, if you don't have data, then the model the model progresses, relaxes toward the background model, and so should the errors. So in the absence of data, the model error covariances should relax to the error covariance of the background model. Now to determine this, Now we created an ensemble of these ionospheric forecast model runs, the IFM model runs, varying all these uncertain parameters, the wind, the electric field, the neutral compositions, and so forth. Now we did 1,107 runs of these of this model to create three-dimensional electron density distributions that we then used to calculate what the Q matrix was. Yeah, so we used to estimate the process noise. Yeah, an important thing to do. Yeah, here's a known output, typical output of this model. You know, where on the right-hand side here, it shows, you know, the GPS data that were assimilated. There are also some other data from ionosondes assimilated. And on the left side here, you see the three-dimensional character of this latitude, longitude, latitude, longitude here, and altitude as we go through the ionosphere in terms of the electron density. You see TC, and you see NMF2. This is the peak density of the ionization. So this peak in the density at about 250, 300 kilometers that I pointed out before. Yeah, so that's a typical output here. Now, the second model that I like to talk a little bit about is an ensemble Kalman filter model. Yeah, that's one of the other models. Now that is way more sophisticated than the Gauss-Markov model, and of course the ensemble Kalman filter. Now that's a Monte Carlo approach, where you sample the probability density for functions of the forecast and the analysis based on an ensemble of model runs. Yeah, I'm sure you had talked about all the details in some previous talks. Now, what this for us does, that allows us to incorporate ionospheric physics in the data assimilation itself. Yeah, that's in the Gauss-Markov model, we could not do that. Here we have the full physics now in the data assimilation system itself. Yeah, now the model behind that is a model for the ionosphere and plasmasphere. Plasmasphere is a region above the ionosphere. I haven't talked about that yet, but this model contains both of these regions, the ionosphere and the plasmasphere. And as a result of having the physics inside of the data assimilation system itself, we are able not to only get specification of the ionospheric plasma density, so the electron density and these densities, that contain to the charged particles, but we also get information about what drives these distributions, what changes them. Yeah, and that is information about the electric fields, about the neutral winds, about the neutral composition that are unobserved in our case, but that are behind changes, or that are behind the observed morphology and dynamics in the plasma. Yeah, and that's, of course, comes from correlations that are built up based on the physics-based model. Now, that's the big advantage that you get here compared to the much easier Gauss-Markov model. Now, just as an, you've probably seen something similar before, how an ensemble Kalman filter works. You start with randomized initial conditions, you propagate this forward with your model. So you get an ensemble of model runs, of model output. You use that to calculate, with statistics, to calculate the covariances that you can then use to calculate the Kalman gain. And this, of course, calculation of the covariance that in the full Kalman filter is a computationally very expensive step. And that's where the power of the ensemble Kalman filter comes into the picture, that this becomes computationally tractable. Once you have the Kalman gain, you take measurements and you can update your states and go back here and go through the assimilation cycle. Now, the ensemble Kalman filter. Now, in our case, forcing of these electric fields or winds and composition plus their uncertainty are the largest uncertainty in this process. It's not so much the initial conditions, it's much more these external forces that matter. Now think of, I showed you before, changes in the temperature in the thermosphere. It changes by 1,000 Kelvin, based on what the sun is doing. So you might get an appreciation how important these driving forces are. And the way how we incorporate these is that we augment the state and we make these values part of the estimation process. So the driving forces are included in the state vector. So the state then exists of the electron density on a latitude, longitude, altitude grid, but we also have neutral density in there. We have the electric fields in there. We have the neutral winds in there. So the driving forces become part of the estimation problem. That's a very important advantage of the ensemble Kalman filter here. Similar things can be done with for DVAR, for example, and JPL has a system like this. Now, when you do an ensemble Kalman filter, there are, of course, you sample the go through the probability density of a function. You sample it. And of course, you take shortcuts there. You're not using millions of model runs. You maybe use the tens or hundreds of model runs, and when you do that, you create spurious elements or spurious contributions in the covariance matrices that can be very problematic, and you have to try to eliminate these. And there's this paper here, that says, that these spurious covariance contributions need to be eliminated, and this might be required in realistic applications when the system dimension exceeds the ensemble size. And that's certainly for us the case. The ensemble size, we're using something like 25 or 50 ensemble member, or sometimes 100, but our system dimension is, there are hundreds of thousands of grid points. Now, a typical way to do this is that you use a Gaussian localization function, which is applied to the state error covariance matrix by means of a Schur product, which means that you multiply each element of the error covariance matrix by some exponential factor. That's where the horizontal distance between grid elements is in there, and also some localization radius are 0. That's a typical way how to do this. So you just say you're correlated to some neighboring points. Now, in our case, things are a little different because electric fields play an important role. I told you before, in the dynamics of the ionosphere. And electric fields, well, that's a more global thing, and they interact. They have now the force and interaction of the electric field and the magnetic fields. So once these lines here, these are magnetic field lines, and you see here that we are along a magnetic field line here. Let's take the outer one here. That if you have an electric field, just basically due to the nature of the magnetic field, everywhere the same along this magnetic field. So if you have it here, it also affects the region here, and it affects the region here. And with this, these electric fields, or the correlations, can become very large, and you can have a correlation on this side of, you can have a variation on this side here, maybe in the southern hemisphere, in the ionosphere, and at the same time, you see a variation in the northern hemisphere at the same magnetic latitude due to these electric fields. And that's something that needs to be taken into account. So one needs to understand the system very well, to not just take maybe the closest neighbors into account. One needs to take a little bit the physics into account, but one needs to be careful there. Always good to go back to the data and see what these correlations are. And that's what we did.
Ludger,
yes.
You have 15 minutes.
15 minutes, that should be good. Yeah, thank you, Geraldo. Thanks. So we determined this localization length. Now, when we looked at spatial correlations of day-to-day TC variability. Yeah, and again, we went back to the data, GPS ground-based receivers. We used thousands of these GPS ground receivers, millions, 150 million of TC measurements, and then determined correlation lengths based on where we are on the globe at mid and low latitudes. Daytime, nighttime was different, different seasons, and different directions. Yeah, and I just like to give you an animation, show you an animation of this here. So this is the correlation coefficient, for different seasons here. Just go through this again. This is the reference point, and then you see a correlation with other regions on the globe, and you see here this conjugacy that you again go through here. I can't stop this, but you have a reference point here, and you see it's correlated to the opposite hemisphere. Yeah, so just a simple correlation radius also would not suffice here. It would not be enough. You have to take some of these electric fields into account, and you have to determine these lengths, the correlation lengths based on data. Important thing when building these systems. Yeah, so these are these correlation lengths. Here is the magnetic latitude of a reference point. This is a magnetic latitude in general here, so you have a reference point, let's say here at 50 degree magnetic, you see it correlates to this region in the opposite hemisphere. So you have a variation in the ionization, let's say 50 degree south, maybe in Chile or somewhere. And at the same time, you see variations in North America. Yeah. And you also can do this here in longitude, and that's more what one might expect, somewhat like 30 degrees here, but you see here that this depends on the latitude. Yeah, important I think it was to go back to the data to determine this. Yeah, we show you an example now of these ensemble Kalman filter that takes all these into account. It's for several days, a couple of years back. This was a stormy period. No, it was a geomagnetically quiet period. I'm sorry. Later on, it was stormy, but this was geomagnetically quiet. So we assimilated data from ground receivers and then used other data for validation that we withheld from the assimilation itself. And you see here, this is, again, it's the peak of the electron density. And you see how this varies through the course of the day. You see, let me just play this again. Play it again. How this varies through the course of the day. You see here the profiles of the black things here with arrow bars. These are observations. You see, you get a little bit of an idea of the dynamics of the system. So these data here were not assimilated. Independent observation, always very important to do independent observations. Yeah. Now I told you that we're not just getting the electron density out of this, but we also get information about the wind system out of this. This is unobserved here. And this shows you, for example, for December, for March and June, different universal times here. We also get for what type of a wind system we get out of here. This is the wind along a magnetic field. Yeah, so it's a certain direction. The magnetic field plays a big role in here. Yeah, and that I showed you before. This is the magnetic the direction here of the magnetic field. Yes, the geographic equator and the magnetic equator. This is magenta color here. It's a little off from the geographic equator. So this is the wind in this direction here. So what we did, it would be very nice to get the wind in all directions here. Not just getting in along the magnetic field, but also get it in the meridional direction, get it in the zonal direction, also get it in the altitude direction. And for that, we build a second data assimilation model. Now, we put on top of what I showed you before with the ensemble Kalman filter. So it's a two-step process where we start from the ionospheric observations, and we have a vast amount of these data. GPS, ionosondes, measurements in situ from satellite. We assimilate these in our ensemble Kalman filter here. As a result of that, we get information about the magnetic meridional wind out of it. Also get other information out of here, about the electron density and diffusion velocity, so on. But now we're not stopping here, but we developed a second model that we call the thermospheric wind assimilation model, that now assimilates not real data, but the output from this model. So we are simulating this into T1, and physics in here helps us to split this into the meridional and the zonal wind. So we get much more information out of this. So again, there's a physics-based model behind it, that has all the forcing on the neutrals included here: Coriolis, gravity, pressure gradient force, viscosity, and collisions. But again, the data is not direct observations of the neutral wind, because that's very difficult to measure in the upper atmosphere. But instead, we're using this wind estimates from the ensemble Kalman filter. And the output then is the zonal and meridional wind out of this. Now, when you look at an equation like this, there's the viscosity term in here, and this makes it a little difficult to solve this. And a typical way to solve it is to use an implicit scheme. Now, if you look at the Kalman filter is generally written for explicit schemes. Explicit ways of how to solve this. Now, what that means, implicit means that all the terms on the right-hand side here, when you difference this equation, are expressed at the new time step. You go forward in time here, and you express everything on the at the new time step. Now, that's of course not known yet. That makes it harder to solve for. In explicit scheme, how the Kalman filter is generally written, this is expressed at the old time scale where at the old time step where everything. So for the implicit, now the advantage of that is that you can use a much larger time step. In this case here, we can use 15 minutes, for example, as a time step. And we use an implicit scheme. On explicit scheme, we would have to use a second or a sub-second to make this, to solve this in a stable manner. So what we did is that we used something that's called the implicit Kalman filter. And the implicit Kalman filter is similar to the traditional Kalman filter, but there are some transformations and some changes of the variables involved. And I don't want to go through the details here. I know this was being made available. This is recorded. You can always go back to this if you ever run into this problem of having to deal with implicit equations. There's of course the measurement equation. That's the predicted state. The measurement equation here. The forecast error covariance forecast. You can calculate the Kalman gate, and you can update your state and the state error covariances. But it's a little bit more involved here. Well, it's actually quite a bit more involved here than just using the traditional Kalman filter. There are transformations involved here that need to be included just for completeness. So if we get this, we get information about the meridional winds. We get information about the zonal winds. And of course, all of these is not just static, it's changing with time. This is the evolution of the zonal and meridional wind here on the globe that we get out of this. This is for a seasonal average here at 250 kilometer altitude. And we've also compared this very important now with yes.
The poles are out of the domain integration here.
Oh, okay. Oh, I should have said something about that. Yes, the assimilation was here for low and mid latitudes. At the poles, we used a different scheme. Because the poles, there's some different physics going on. At the poles, electric fields the electrodynamics becomes very, very important, even more important than at low latitudes. So one needs to directly include that in the the data assimilation there. So this is only for low and mid latitudes in here.
Okay, thanks.
Absolutely. Yeah. Thanks for pointing that out. Yeah. So of course, comparing with independent observations, always critical. You know, when you do data assimilation, that is one of the most important steps to do. Yeah, and so this is a comparison here with so-called Fabry-Perot observations. There is a handful of these instruments located around the globe. They can only give you information at nighttime, very limited. But you see here the comparison with what we get from the data assimilation, based on ionospheric observations. Now I'm talking about the neutral wind here, totally unobserved quantity, and we get a fairly good agreement here. This is for the meridional wind and also for the zonal wind. Now, and I should probably stop here. I have a little bit more about what we now do. Now we have this host of data assimilation models, and the next step, what we did was to do something that's called multi-model specification and forecast, or MAPS, and the multi-model ensemble specification and forecast or MAPS, where we now combine the specification and forecast from various models. But let me stop at this point and see if there are any questions.
There is some questions in the chat. By the way, I did most of them. But to me, I wonder something about, if not related to data assimilation, but the forward problem. Can you simulate the ionospheric bubbles?
Ionospheric bubbles. No, ionospheric bubbles.
In particular, on Brazil, this is very important.
Right. This is. I said before that for GPS, for example. So ionospheric bubbles. Let me go back. Well, to give you the answer already, no, we do not simulate ionospheric bubbles, but just for the general audience. Yeah, if you look at these, this is the ionosphere, typical profile during the daytime here. And then at night, I know when the night sets in, then the ionization, the production stops, and the bottom part of this profile here basically goes away. The ionization recombines with the neutrals, and the ionization goes away, and that makes very steep gradient at the bottom side here. So this sometimes people compare to as a heavy fluid sitting on a light fluid, and then you have a little perturbation on the bottom side here, and that creates an instability. Like you have a heavy fluid on a light fluid, you shake it a little bit, and there are bubbles going up through that. It becomes unstable. We have a similar situation in the ionosphere, especially at low latitudes, where this layer then sits on the magnetic field and is basically held in position by it. This leads to scintillations. When now a radio signal moves through that layer, it becomes very turbulent here, and that signal becomes strongly affected, sometimes totally unusable. So GPS becomes unusable, and these are the bubbles and the scintillations, and these are small-scale features where even many of the physics is not fully understood yet, like the trigger mechanisms. What triggers this instability down there? So that's not part of these models. But it has been shown in the past that an important parameter behind this is the electric field. And electric field is something that we get out of our assimilation. Also, the wind plays a role in there. So that's something that we could use to come up with maybe a probability of occurrence for bubbles, but the bubbles itself we do not model.
Okay, And how about the extreme ultraviolet estimation? For example, if you are using solar 2000 schemes or LVAC, there is a lot of difference. And so data assimilation can help us to have a better estimation for this very, very important issue for ionospheric simulation.
Right. That's also, it's not part of this model. So we're not having like the EUV spectrum as part of the state to estimate. The thing is that the radiation coming from the sun, for the other people, there are uncertainties extreme spectral regimes, and that has different effects at different regions in the ionosphere. Some propagate deeper into the lower altitudes, some are absorbed higher up, and leading to differences in the profile. And of course, the important thing, in the future, maybe with radio occultation measurements where we have profile information, much more, that's coming very, very strongly now. There are, when I showed you results here, that was with cosmic radio occultations, but there's much more now. Cosmic 2 has thousands of radio occultations per day. Now there's Spire occultation, radio occultation network, and so in the future, that's something where I think data assimilation could help by including at least certain parts of the spectrum in the estimation problem. There are some attempts where F10.7, for example, which is a proxy for the EUV emissions, where people put that in the state and estimate what would be an approximate, or what would be a better estimate for F10.7. And that more relates to what we see in the ionosphere. That's something that goes in that direction, but there certainly is a lot to do, and we need the right data to do this.
By the way, I used to say radio desoccultation instead of radio occultation, because instead of use radio occultation, I used to say radio desoccultation. Because you can see, well, we can recover the information that there is no the satellite that one each other can see one each other, because in the right line. Okay. So I used to say desoccultation, but this is it's a joke. Okay, thank you very much, Professor Ludiger, for your amazing talk. Teach us about the ionosphere, all the complexity inside this, and so this that you have using different approach for data assimilation in order to have a better results for this very, very important and very important application here. Thank you very much.
Oh, I hope it was helpful to the PI. I know it's a broad range of people listening to it, so I hope it was at least a little bit helpful.
Okay, and so probably I'm going to bother you with other emails, because I have 100